Good morning. Thank you all for joining me today. My name is Michael L. Perry. I am a Pluralsight author and a software mathematician at Improving. This is a company based in the United States. And because of my love for math and for solving problems, I am proud to present Git as blockchain. This is a story about a group of friends. These friends like to go to lunch, and you might have friends just like these. They all work at a software development shop. They all like to enjoy friendly conversation and try to solve the problems of the day. So I'd like to introduce you to them right now. Up there at the top left, we have Daniel. He's very clever, he's opportunistic, and he loves to figure out the best kind of solutions for his friends. And then just below him, we've got David in the red shirt there. And David is an organizer, and he's incredibly helpful. And then up here at the top right, we have Thomas. Thomas is helpful, and he's eager to please. And then finally, at the bottom here, we have Tim. And Tim is very supportive and loves to provide the tools that his friends need to do their jobs. So as they're finishing up with lunch, Tim goes to pick up the check, and Daniel says, "Wait, no, you picked it up yesterday. It's my turn. How are we going to keep track of whose turn it is to pick up the check?" Of course, at no point does anybody decide to split the check. That would just be silly. That would be way too complicated. Somebody has to pick up the check. But who will it be? David comes up with an idea. He says, "I'll keep track of things in a ledger, and we will use this ledger in order to decide whose turn it is to pick up the check." So in this ledger, I'll keep track of transfers. And so the transfers will look something like this. They will have each person who was at the lunch, and then how much of the ticket was their lunch, and then for the one person who picked up the check, what was the total. And so we'll end up with a series of transfers that look something like this. The value that is your part of the lunch is value that is coming from you into the system. And then the value of the total of the check, if you pick it up, that's value that's coming to you. So all of the transfers from everybody has to add up to all the transfers to everybody else. And so if we have a series of transfers where the froms and the tos are all equal, then we have a balanced lunch. Balanced lunch, problem solved, everybody's happy. But then, of course, Thomas asks, well, how is this going to help us decide who's going to pick up the check? So Daniel says, well, from this, we can calculate a personal balance. So if we keep track of these transfers from lunch to lunch, then we'll have all of the transfers from people where they were, which were their portions of the check, and we add those all up, and then also add in the transfers to those people, which is when they picked up the check, and that will give us their personal balance. So we'll have a whole bunch of personal balances for everybody, and the person that has the lowest personal balance is the next one to pick up the check. Sound fair? Okay, yeah, that all sounds good. Oh, but wait a minute. Wouldn't that mean that people could have a negative balance? David says, well, sure, yeah, negative numbers are fine. What's wrong with that? And then Thomas says, well, if somebody had a negative balance, then they could just simply decide to stop going to lunch. So we've bought lunches for them, but then they'll never pick up the check on their own, and so we're out that money. So we have to protect ourselves against these negative balances. Okay, all right, so David comes up with another plan. He says, we'll have a bank. So everybody will just buy in for $40, and then that will start you at a positive balance. And so now whenever your balance is approaching zero, you go ahead and pick up the check. That increases your balance again. And so now nobody ever has a negative balance. Okay, all right, that sounds good. And they continue in this way for a while, and they are never at a loss for whose turn it is to pick up the check. So time passes, more people join the company, and so here we have Vaughn in the center. Vaughn is incredibly creative, and he's a very helpful person. And then up here at the top we have Corey. Now she is absolutely brilliant. She knows Git inside and out. She is an expert. And then down here, here we have Harold. Harold is a well-intentioned troublemaker. He likes to see what sort of things he can get away with. And so we have more and more people going to lunch, which means that we don't always have the same group at lunch, and that means that David, with his trusty ledger, is not always present. And so Daniel goes ahead and grabs the ledger, and he makes a copy. And then Vaughn takes Daniel's ledger, and he makes a copy as well. And now we have 3 different copies of the ledger. So as long as David, Daniel, or Vaughn is at lunch, then we can figure out whose turn it is to pick up the check. All they have to do is every day they consolidate. So David will have his lunches that he picked up that day. He'll share them with Daniel. Daniel will share those lunches and his own with Vaughn. Vaughn will share his lunches and Daniel's back to David, and they'll go around and they will consolidate their ledgers, just simply appending those new lunches that they each don't know about. More time passes, more people join, and we get more and more copies of the ledger. So every time somebody joins in, they have to find somebody every day to copy the new lunches from. And then somebody else will copy those lunches back into the other ledgers. And so it goes, copying these transactions one to the next. Finally, they decide this is far too much to keep track of. And so Thomas pipes up and says, let's use Git. Git can solve this problem for us. Here's how we'll do it. So he creates this file. This file is just simply a section for each of the different lunches. And then within each section, we've got a line for each of the different transfers. So we start off with a section that's a bunch of buy-ins where people bought in for $40. And the bank, in order to balance that, had to lose value of $240 to balance things out. And then we had lunches for where each of the different participants lists their portion of the lunch, and then the person who picks up the check lists the total. Now we've got this large file that we can check into Git. And now instead of copying by hand, ledger to ledger, we can just create remotes for each other, and we can pull from those various remotes. Now, of course, at no time do they think to just use something like GitHub. No, you can't trust some central repository like GitHub. You have to pull from all your friends. So they create these peer-to-peer networks. Now, as part of this file, they have to make sure that each of these different sections is valid. So first of all, it has to be correctly formatted. But secondly, the sums of each of the different transfers within each section has to be 0. And so Tim creates this validation program. He writes it in Node so that everybody can just simply run it on the file that they've got on their machine. So he creates validate.js, and now you can just run node validate lunches.txt, and it runs the validation checks, make sure that that all of the sections sum to 0, and also make sure that nobody's balance falls below 0. And if those things are true, then it says OK. And so now all they have to do is make sure that they validate every time that they get a new lunches.txt, and everything's going to be good. In order to calculate the personal balance, Tim also creates a balance.js. So this is another Node application where you give it the name of the person and the lunch file, and then it will run through all of the different transfers to and from that person, add them all up, and show you what their personal balance is. So this is already built into the validation where it makes sure that their personal balance is above 0. But this way you can just run the balance script for each person who's at a lunch, figure out who's got the lowest balance, and then they can pick up the check. So now he goes ahead and checks these into the same repository. So everybody has a copy of these node applications. They can run them in whenever they want to. And now the daily consolidation just becomes a pull from all your different friends rather than a copy of the ledger. So when you pull from one of your friends, you want to make sure that you only pull valid commits. You want to make sure that the lunches.txt file that they've got in their commit runs the validation program correctly. And so Corey comes up with a clever idea. She says, I'm going to create a Git hook. So this is a little script that you just add to your Git repository. You don't check it into the repository, so it's not shared with everybody. But this is just a script that will, every time you merge, which happens on pull, it's going to run node validate lunches.txt. So it can't reject the merge itself, but if validate prints out reject the commit, then you know to just go ahead and reset and tell them, nope, I can't accept that commit from you. So she creates this little Git hook, and then she asks all of her friends to go ahead and create the Git hook on their machines. And now everybody is running the validation program every time they pull. So it looks like we're well on our way to a very good solution for keeping this distributed ledger so that we can keep track of whose turn it is to pick up the check. Unfortunately, we run into a small problem. Since we're appending each one of the lunches to the same file, we start to have these merge conflicts. We have this hotspot at the end of the file where everybody's trying to add new lines. And so whenever you pull from one of your friends, you might get one of these merge conflicts if you were at a lunch that they weren't at, and vice versa. So, so then you have to figure out how to resolve this merge conflict. And so you'll say, okay, I'll just accept this lunch before that lunch. We'll append them in this order, and everything will be good. Now, since everybody is pulling from everybody else, then this same merge conflict might happen someplace else in the network, and they might decide to resolve it differently. They might decide, well, let's pull the right before the left instead of the left before the right. And so now you've got not just these merge conflicts, but you've got more merge conflicts of those merges, and chaos ensues. And you can never get this file down to one single order that everybody agrees upon. So Corey comes up with another idea. She says, well, since we can't reliably append to a single file and avoid merge conflicts, what we'll do is we'll just break up the file. So for each lunch, we'll create a brand new file. So this file will just have all of the different transfers that happened during that lunch. So we've got all the people who were at the lunch, the portion of the check that was theirs, and then for the person who picked up the check, we've got the check total. So now we can validate this individual file, make sure that it sums to 0, and we can then validate the aggregate of all the files and make sure that overall the history, nobody's personal balance goes below 0. So we've broken it down, we've resolved the merge conflict, because immutable files have no merge conflicts. I made this big because it's important. So Tim modifies his validation program, and he says, okay, now instead of validating one files.txt, we're going to validate a whole bunch of files. So every file that was added during the commit. We'll go ahead and validate each of them and make sure that the sums of the transfers within that file is equal to 0. And then we will also validate the balances. So everybody's personal balance greater than 0. If that all checks out, we print OK. If not, we print reject the commit. And then Corey makes one more change to her Git hook because, remember, we want to make sure that these files are immutable. And so she modifies the Git hook so that it looks for files that were modified or deleted. And if it finds any, it says reject the commit. And those little control codes right there make sure that they shows up in red so you can see. You need to reject this commit. So after it checks to make sure that there are no modifications, no deletions, then it runs Tim's validation program. And then everybody can be sure that if they pull from one of their friends and this thing does not print reject the commit, then nothing's been changed, nothing's been deleted, and everything is valid. All the balances are above 0, and all of the sums of the transfers are 0. So everything seems to be working out pretty well. Until Harold gets an idea. So Harold's balance is getting kind of low. He decides that, you know what, that's not quite enough for me to have lunch on today, but I'm a bit low on cash, so I can't really pick up the check and get my balance back up. So here's what I'll do. I'll go to lunch with the early crowd. We'll head over to BJ's and I'll pick up a salad there. And then, after they get back, I'll join in with the late crowd and we'll hit McAllister's. And at McAllister's, I'll go ahead and pick up some soup. So now I've got a complete lunch, but I spent less than my balance at each place. Now, since they didn't have time to sync up with one another, neither one knows that my balance has gone negative. So they both accept the commit. So, yeah, this is a perfect plan. Let's see if I can do this. All right. So Harold goes to lunch, then he goes to lunch again. And after he gets back that afternoon, the two groups try to pull from one another. And they find that their commits won't merge. That the validation program says, reject the commit, because Harold's balance is a negative. So they all turn to Harold and they say, what are you trying to do, man? Come on, we got a system working here. And you're just trying to game the system. He says, well, no, I'm just playing by your rules. This is how this is supposed to work, right? Say, no, this isn't how this is supposed to work. We're supposed to play fair. And so they learn a very important lesson this day. No, the lesson isn't that Harold can't be trusted. He's just a fun guy. What they learn is that you can't allow merges. That you have to have a linear history. You have to decide the order in which these commits actually happened. If you allow things to branch and then try to merge them together, then you might find that neither side can accept the commit. But if you create a linear branch, then you have accepted one. The next one that comes along, if Harold's balance has gone negative, you have to reject that one. So it helps you to make that decision. Now, what happens when you reject that commit? Well, that's between you and Harold. If you can get him to pick up the check on the next try to kind of balance things out, then that's all for the good. But there is no arbitration. It is completely up to you to figure out how you're going to resolve that problem. But the question still remains, how do we decide which is the correct branch? So David has gone to lunch with Harold. Yes?
Sorry, just one question. I mean, I'm trying to follow all the timeline. It's really, really interesting. Just the rule that you said, why Harold wasn't made to pay the lunches if his balance was low? Why did someone else pay the lunches? Those days. Shouldn't have, because his balance was low and
Yeah, so
balance is the one that picks the check, right?
yes, but let's just suppose for the sake of argument that somebody else's balance was lower. So, yeah. Yeah, sometimes these have to be a little bit contrived to make them work, but yeah. So, so yeah, how are we going to decide which of those two branches is the correct one? So we have to pick one and then put the other commit on top of that branch, or at least try to. So we've got David, who went to lunch with Harold at McAllister's, and Daniel, who went to lunch with Harold at BJ's. and we need to figure out who's going to win. And so again, Corey comes up with a great solution. She says, I know, we'll vote. The way we're going to vote is that we're going to just assume that one or the other is the valid commit, and then we're going to build on top of that. And then the more lunches that we get on top of the one that we think is valid, then the higher that collection of votes. And so that means that the winner is the longest chain. Sound good? Okay. Yeah, so then what do we do with all of those commits that were on the chain that didn't win? Well, we just have to cherry pick those. So yeah, we could try to rebase, but we'll find that Harold's commit right there is rejecting the whole chain, so we'll just throw Harold's commit to the side, and we'll cherry pick the ones that will merge with our history. So, okay, so we've got a nice long chain of commits, and we know that every time we cherry-picked a new commit onto it, the validation ran. Those commits that we couldn't add to our history, we just have to figure out what we're going to do about those. There's no arbitration on the history itself. There's no central bank that's going to, or I shouldn't say bank, but there's no central authority that's going to decide how to resolve this conflict. It's just between you and Harold. So, all right, we've got the longest chain winning, and then Daniel sees an opportunity. He sees that he can make one small change. He goes to lunch, and he's running a bit low on cash, so rather than having his own name there in the commit, he can just simply change that to David's. So now David's balance goes down and Daniel's doesn't. Hey, everything's good, right? He even goes so far as to fake the author. So when he commits, he says, oh, you know what? David actually committed this. And so this gets into the repository, people pull it, and then David eventually figures out, wait a minute, my balance is too low. What happened here? And he goes back through the history, and he sees a record that he went to lunch, and he says, I know I didn't go to lunch that day. And so he asks the other people who were at lunch, and they were like, well, yeah, I remember that you weren't there, but I'm afraid so much time has passed, I can't remember who was. So Daniel never gets caught. But everybody knows that somebody is gaming the system. And so they're looking over each other's shoulders, trying to figure out, are you being fair? Are you writing down the right things? Are you faking somebody's name? And then Tim says, wait a minute, we have a tool for this. I'm going to generate a public key. So he sits down and he generates a key pair. So he's using OpenSSL to generate an RSA key. And then from that RSA key pair, he generates, he extracts the public key. So now he's keeping track of both of these things in his own private folder. This key pair doesn't make it onto the repository. He's just keeping track of that on his own. So this is what the public key looks like. That's in his own little folder. And now, of course, this is an awful lot of information, but he does need to share this with other people. What he wants to do is identify this public key with something shorter. And so he creates a fingerprint. He takes a SHA-256 digest of that public key, and then that digest, that's still a reasonably long number. He just goes ahead and takes the first 7 characters, the first 7 digits of that digest, and he says, okay, that's going to be the fingerprint. I will use that as a really short name for that entire public key. Now, the reason that this works is because, first of all, if you were to take the digest of the public key yourself, you would get the same hash, and you would be able to see that same prefix. But the reverse is very difficult to do, given these 7 characters, it's very difficult for you to find a public key that will give you that same fingerprint. This is a one-way function. It's a hash. So this fingerprint is a nice little stamp. It's a nice little indication that this is my public key. And now everybody can verify those fingerprints. So using OpenSSL, they can take the digest of your public key, and they can make sure that the digest starts with the 7 characters that are the file name for that public key. So all he needs to do is share this around with everybody as part of the commit. Now, he also says, let's go ahead and change the lunch file. So rather than putting people's names in there and having to remember whose name belongs with whose public key, let's just put the fingerprints in there. So now you know that this fingerprint belongs to some public key, and then that public key belongs to a person. We don't identify that person in here, but that person ate lunch for a certain amount, and then some other fingerprint of some other public key represents some other person who picked up the check for this total. So we've hidden the names, so you might say that this is anonymous. However, we still have all of this history. Yes?
So the person who, or the fingerprint who picks up the check here is actually not, having lunch?
Ah, yes, this was another simplification that Tim decided to make. Rather than having 2 transfers, one negative, one positive, he just added the values together. So the only thing that really has to be true is that all these numbers add to 0. So you could have their lunch portion, like suppose they had a $10 lunch. So you could have negative 10 next to their fingerprint, and then $46.59 as the check total. But he just decided to simplify it, do the math, get that one transfer out. Yeah, good question. So you might think that, yeah, this is anonymous because I've hidden people's names. But since you have all that history, you can still kind of go back and figure out who is who, just by seeing who had lunch when, and then asking the right people, and then doing a little bit of research. You can reconstruct identities. So it's not anonymous. You might call it pseudo-anonymous or pseudonymous. But at any rate, we just use these fingerprints to represent identities. And now everybody can take this new lunch text file, and they can sign it using their private key. Now, the private key is kept on their file system. It's not part of the repository, so only they have it. So they use OpenSSL. They grab the digest of the file using SHA-256, and then they run that through their private key, and that creates a signature. And so they create a new file with that signature using their fingerprints, and that now is a signature of that lunch file. So everybody creates these. Oh, yes.
Would it just be easy to enforce that people sign the commits that before they push up?
Excellent question. Git does have this this awesome feature where you can sign commits. The commit is signed by the one person that pushes it. What we're trying to do here is have everybody who participated in the lunch sign this commit. So that feature that's built into Git wouldn't work in this case. So now that we have all of these signatures, everybody can verify each other's signatures. So they take the SHA-256 digest of the lunch file, and then they verify that this public key matches the signature of that lunch file, of that digest of that lunch file from this particular signature file. So run that all through OpenSSL, and it verifies the signature. So now we've got this entire set of files. We have all of the different signatures. We have the lunch file itself, and then we have all of the public keys of all the participants of that lunch. And we commit that all into the repository. So this commit is just simply creating all of these brand new files. If your public key was already in the repository, then it hasn't changed. You don't have to add it again. You don't have to modify it. So it just simply is in the repository already. So we still have commits that are themselves immutable. Everything is just additions, no modifications, no deletions. Now, this is a lot of information to validate, so Tim updates his validation app. And now we're validating not just the lunch file, but we're also seeing all of the fingerprints that are in that lunch file. And then for each of those fingerprints, we're validating that we have a public key file. And then we're taking the SHA-256 digest of that public key file, making sure that it matches the fingerprint that is that file name. Then we're using each of those signatures to validate that those public keys actually match the private keys that were used to create those signatures. And then we are computing all of the personal balances of all the participants of the lunch, making sure that nobody has gone negative. And if all of that's good, then the commit is okay. And if any of that fails, you have to reject the commit. So, finally, Tim updates the balance script in order to compute the balance not by a person's name, but by the fingerprint of their public key. And so now he can compute those balances. All you have to do is when you go to lunch, you just share fingerprints with one another, say, yeah, this is my fingerprint, and then you can all validate the balances, figure out who's going to pick up the check, and then start this whole process. Simple. But Thomas is getting a little bit frustrated. He says, this is too much to keep track of. I don't want to have everybody's history. I'm just one person. I'm just going to lunch every once in a while. I don't want to keep track of all lunches. And so Corey has an idea. She said, why don't we just create one folder per person? So what we can do is we can use their fingerprint as the folder name. And then once we have folders, we can use get subtree to split those folders. So if you've not used get subtree, this is kind of an arcane little command, but comes in quite handy, especially if you're splitting a large monolith up into smaller services. But a get subtree split will take one of the folders within your working set, and then it will go through all of history and find all of the commits that changed a file within that folder. And then it will create another commit that is only the changes to those files. So now you've got a parallel history that's going on, which are just those changes that affected that subtree. And then at the end of this, you end up with a SHA that represents that final commit. If you were to check out that SHA, then your working set wouldn't be the full directory, it would just be that one subfolder. And so using get subtree split, Corey was saying that what we can do is we can grab just the commits that affected your folder. And then when you check it out, you'll only have the files that are in your folder. So she runs this command, and then she creates a new branch at that commit, and she calls it wallet. So you can think about your wallet as kind of this history of the changes that only affect you, and the private key pair that you've got stored off on your file system. So these two things together, you can kind of think of as your wallet. Now that she has this wallet that just represents the things that affected Thomas's balance, Thomas is able to pull from that, and so she copies. So every time they go to lunch, they create a copy of the lunch file in everybody's folder that participated in that lunch. And then within that folder, we keep their public key, and also within that folder, we keep their signature of that lunch file. So again, this is still a commit that just creates a whole bunch of new files. It doesn't modify anything, but now we have the commits kind of broken up into different folders representing the different people. Tim has to make one small change to his validation program. Now that we have several different copies of the lunch file in several different folders, he has to validate that all of those copies are exactly the same lunch. So Git, behind the scenes, it's going to be creating just this one object and having these 3 or 4 different pointers to it, but we can't really see that from the file system. All we can see is that we've got 3 or 4 different copies of this one file. And so we have to validate that they're all the same. And then we can continue the rest of the process, validate those signatures within those folders, validate the public keys that they have the correct fingerprints within those folders, validate the balances, and everything's good. But then, Thomas goes and pulls that wallet subtree from Corey's repository, and he finds that that commit won't validate. It says that somebody else's balance is negative. He scratches his head trying to figure out what happened, and then he realizes, oh, I don't have any of their history except for the lunches that they went to with me. So only the subset of history that actually interacts with mine, that's all that has shown up in this wallet. So given just a wallet, I can't really validate all of history. I have to rely upon somebody else to do that validation for me. So Thomas says, well, I suppose that's worthwhile. I really don't want to keep track of everybody's history. So even though I can't validate everybody else's balance, I'll just go ahead and turn off my Git hook. That doesn't affect anybody else. It's just I'm not going to be running the validation every time I pull from somebody. I'll just rely upon them to have done the validation for me. So this goes on. More and more people decide, yeah, they really just want a wallet. They just want a subtree. They don't want the entire thing. And then Daniel sees an opportunity. He says, hey, there are a lot of people that don't want to do all this work. So that means that they must have some value that they assign to the work. They must be willing to pay a little bit for me to do the work on their behalf. So here's what I propose. He says, let's go ahead and create a payment for each transaction. So at the end of each transaction, let's go ahead and decrease the bank's balance by $1, and then we can increase my balance by $1. So I take $1 from the bank. Even on those lunches where I didn't participate, I wasn't there, I didn't pick up the check, I'll go ahead and take $1 for processing this transaction. And Vaughn says, hey, wait a minute. You're not the only one who's going to be processing transactions. I'm going to want to get in on this as well, so we can't have this as part of the lunch file because everybody is signing that lunch file and it's got your public key in it. No, not buying it. So Daniel says, okay, let's go ahead and separate this from the check. Let's say that we've got the check, which is just what happened during that lunch, but we'll create a separate file that has just the transfer from the bank to the person who happens to process that transaction. And that way you get to put in your own public key. And nobody else has to sign this one. It's just when you pull, you can validate that you've only taken $1 from the bank. So nobody at lunch has to authorize that payment. We just make that as a new rule on this network that we're going to allow the person who processes the transaction to take $1 from the bank. So everybody who is at the lunch signs the lunch file, and then only the person who actually processed the transaction signs the withdrawal file. Sound good? Well, not quite. I like where you're going, but if we always take $1 from the bank, then eventually the bank's going to be empty, and we won't be able to withdraw any more money from it. So how are we going to solve that problem? So Daniel asks David, well, how much money is left in the bank? Let's see what we've got to work with here. And David says, well, we had 25 people join the company since we started this process. So at $40 buy-in each, we've got $1,000 in the bank. Okay, we can work with that. So let's suppose that on that first commit, the person who processes that, we've got $1,000 in the bank. they take 0.1% of what's in the bank. So they take $1. So that means that subtracting that $1, we've got $999 in the bank. And so the next transaction will just take 0.1% of what's remaining, and so they'll get 99.9 cents. Okay, subtract that. We've got $998 and a tenth of a cent. Take 0.1% of that, and we get an even smaller fee or withdrawal that we can take from the bank. So as we keep going, we can see that, yes, we are withdrawing money from the bank. The bank's value is getting lower and lower. But we're always taking a fixed percentage from the bank. So that means we can never withdraw everything. It's just going to get lower and lower. It's going to slowly approach zero. Now, that's a little bit complicated to do that math and figure out what's the remaining balance of the bank. So what we can do instead is we can just look at it like this. If we were to take 0.999 of the previous amount, so 99.9% of the previous amount, we would get the next amount. So 99.9% of that first dollar that we took out, that gives us 99 cents and 9 tenths. We take 99.9% of that, and we get the next transaction amount. Take 99.9% of that, and we get the next amount. So all we have to do is multiply by this constant value every time we create a new commit, and that tells us how much we can withdraw from the bank. Everybody can agree upon that one rule, and that way it can be built into the validation system, and we always know exactly how much that withdrawal is supposed to be. And that will set up this exponential decay now. And so the value of the bank won't be depleted after 1,000 commits. It'll just be down to about $368. And so that means that the withdrawal from that point forward will be somewhere around 36.8 cents. Okay, that's fair. So we're not completely depleting the bank, but we're just taking less and less over time. At some point, don't you think that the cost of running the servers is going to be more than you're getting from the bank? And Daniel says, yeah, you're probably right. So how about we do this too? Everybody can optionally choose to add a little transaction fee. So within their commit, they can choose to say, and 5 cents goes to whoever processes this commit. And so now if I'm looking at this transaction and I think that, yes, the value I'm getting from the bank and the value of the transaction fees is sufficient for me to keep running the servers, then I'll go ahead and process this transaction. But if not, I'll reject it. And then I can create this new file that shows that I'm taking my dollar from the bank and I'm taking the sum of these transaction fees. So now it's not the sum of each of the individual files, but the sum of both files together that's going to be equal to 0. So again, all the participants sign the lunch file, and only the person who processes that transaction signs the file where they're taking transaction fees and the withdrawal. So Vaughn, he pipes in. He says, you know what? 5 cents is too much. So I promise that if you put in a transaction fee of 3 cents, I'll still pick it up, even if Daniel won't. And he's thinking to himself, that means that I get all those transaction fees and I get all of that withdrawal from the bank, and it's going to be wonderful. But Vaughn, Daniel can see what Vaughn is thinking, and Daniel says, well, it's going to cost you just as much to run the service as it's going to cost me. So what's really going to happen here is that we're both going to try to figure out the most efficient way to run our servers and then charge just enough transaction fee to cover those costs. If we charge too much and the other person is being a little bit more efficient, then they might take all of the money for themselves. So this is going to kind of balance itself out. We're going to end up with transaction fees that are locked to the cost of running the servers. So go ahead and compete. And that will help us to figure out what those transaction fees should be. So they continue like this. They compete to process these transactions until Harold gets an idea. He says, you know what? I can just create a whole bunch of transactions. And so one day, people come to work and they see all of this history inside of the repository. And they're like, what is going on here? So they look inside those commits and they see that what Harold is doing is he's set up another public key and he's doing a transfer back and forth. Now, he's not charging any transaction fees for these. He doesn't have to. He's just withdrawing the money from the bank. And when people get wise to this and say, wait a minute, no, you can't do this. This isn't fair. So, what do you mean it's not fair? We set up the rules. We agreed to this. This is how it's supposed to work. No, this is not how it's supposed to work. You're supposed to try to play fair. So finally, Corey says, guys, I got this. So she creates the commit for lunch, creates all the files, gathers all the signatures, and then just as she is starting to commit, she slams her fist on the keyboard to generate a random commit message. Everyone's like, what are you doing? Now, she looks at it, frowns, no. And so she resets that commit, adds everything back in, stages it again, and then bam, no, reset. Bam, reset. Bam, yes! And then she flips the screen around and shows everybody, look, I got one. You got what? Well, look at the Shah. You see that? And Harold's like, well, not sure what I'm looking for. Well, the first digit is a 0. It took me a lot of work to get that Shah. You could see that it did a lot of work. And Harold said, yeah, I saw you beating the crap out of that machine. But then Corey says, wait, no, you don't have to have seen me doing the work. This is the work that I actually did, is that every time I did a commit, I would just reset to the commit prior to head, stage everything again, do the commit again. And you scroll up and you see there are a whole bunch of commits that don't start with zeros. But the fact that I was able to get a commit that does start with 0, you don't have to see all of that. You have proof right there in that SHA that I did the work. All right. So we have proof of work. What does that mean? How does that help us? She says, well, if you have to do all of this work in order to get a brand new commit, then that means that we can slow Harold down and he can't just create a whole bunch of these random commits. Because if he's transferring stuff back and forth and he's doing all of this work every time, then eventually one of us is going to come in with a valid lunch and we're going to go ahead and build on top of that chain. We slow him down enough and then only the valid lunches will make sense. He'll have to outrun everybody in order to make his fake history. Oh, okay. Well, then Thomas pipes in, you know what? I can just simply write a script and then I can just do what you did much faster. And so he writes in a script and he says, okay, I'm going to go ahead and mine for 8 bits of zeros. So rather than a single 0 digit at the front, which is 4 bits of 0, I'm going to mine for 8. So let's keep on going. Oh, 215 attempts later, finally, we get a commit that starts with 2 0 digits. That's 8 bits worth of zeros. Okay, so you see, I can mine and I can produce these commits that have a valid SHA, and I've proven that I've done the work. So how is that really going to slow down Harold if he can simply do the same thing? And Corey says, well, if we see too frequent of commits coming out of the system, then we can just simply demand another bit. Because by doing so, that's going to double the amount of work that you have to do in order to get something that's valid. Ah, clever. Okay. So we've got 5 people running this script, and let's suppose that it takes 10 minutes for one of them to find something that starts with 8 0 bits. So that means that if we now get 10 people running the script, it's going to take 5 minutes for one of them to get lucky. So we just demand another 0, and now we're back up to 10 minutes again. I see. So we can use this proof of work to tune the system to produce commits at the frequency that we intend for it to produce those commits. Exactly. So we continue mining the system, and we'll end up with this history of all of these commits that start with zeros. And then as we need to slow the system down because people are putting more and more hardware onto it, we just demand more and more bits, more and more proof of more work. And that keeps things going at a steady pace. And now Harold can't get up to any of his shenanigans trying to create this fake history. Because if Harold just tries to create some fake history, then the rest of the network is going to outpace him because he has to do all of this work, and they've got more computing power among them than he has just on his own. And so his chain isn't going to be the longest chain, and his won't be the true history that everybody agrees upon. We'll end up with this chain of commits, where each commit knows the SHA of the previous one. And so you can say that we've created this chain of blocks, each one pointing back to the one prior. Each commit has a SHA, has a hash of its contents, but it also includes the hash of its previous one, and so that is what keeps this history from being tampered with over time. Each commit knows its predecessor. This is also very important. But just then, Harold gets an idea. He says, you know what? I can get around this problem. So he leans over to Thomas and he says, you know what? If we were to join forces, we could put Daniel and Vaughn out of this mining business, and we could keep all of those withdrawals for ourselves and all of those juicy transaction fees. And you know what? Even better, anytime somebody takes us out to lunch, we can go ahead and reject that commit. We can say, no, we're not going to process that lunch file because that's not favorable for us. That decreases our balance and increases somebody else's. So we will control the history. We'll only put in the history that is favorable to us. We'll get all of that money, and all we have to do is only build upon each other's commits. So Daniel and Vaughn are going to be running their servers out there. They're going to be mining, and even if theirs is the longest chain, we'll ignore it. And we will just build on each other's commits until we've got enough commits there to make ours the longest chain. And then everybody will switch to ours, including Daniel and Vaughn. And so they might go ahead and find another commit at the end of our chain. That's okay. We'll ignore that one too. And then we'll just keep on building on our own. As long as we can keep ahead of everybody, then we'll own the history. We will run the network. It'll be great. So we already represent half of the computing power that's out there. So it's just Harold, Thomas, Daniel, and Vaughn that are running these scripts. So if I were to spin up just one more, then we would have a little bit more than 50%. So all we need is to retain 51%, just a little bit more than 50%, and then we will be able to outpace what everybody else can do. That's pretty sneaky, says Thomas. It takes a little while of them doing this before Daniel realizes, hey, you guys are up to something. And so he spins up another server. So that balances things back out again, but that's all right. Thomas spins up one himself. Okay, now we're back up above 50%. So Corey can see what's going on. She spins up a server. All right, Sarah can spin up a few more. All right, we're back up to 51%. David goes ahead and joins the group. He's not going to align with either party. He's just going to run his own server, but still, that puts more computing power in the system, and so we have to add more and more and more and more and more in order to make sure that nobody can join forces and create this 51% attack on the system. And so we've got this, this group of servers that are just churning away, looking for more and more work in order to prove that they produced more and more zeros at the beginnings of their SHAs, because now we're producing transactions at a higher and higher rate, so we have to have more work to keep the rate constant. And that's going to keep Harold and Thomas from achieving their 51%. So all of this work is going to be going on in order to protect against this attack. So we will escalate until now the cost of running these servers has ballooned, and remember, the transaction fees are locked to the cost of running the server, so now the transaction fees are going up for everybody because you can't afford to run the servers and not collect transaction fees. So, so the cost is skyrocketing. And we've got this set of friends who used to just go out to lunch and have friendly conversations, and they would graciously pick up the check for one another. And they have escalated into this arms race of spinning up more and more servers. Through all of this process, they've come up with some really great solutions here. They've decided to have a shared ledger, that they are going to consolidate that ledger peer-to-peer by pulling from one another. They're going to use public keys and digital signatures in order to verify the authenticity of that ledger. And they're going to create subsets that are just the wallets that they're interested in if they can then rely upon somebody else to do the validation for them. So they've come up with some really great solutions here. But there's one solution that they didn't come up with, and that's this. That's big because it's important. Now, I'm not talking about blind trust. I'm not talking about naive trust, just assuming that people are going to be doing the right things. What I'm talking about is the trust that you get from working with the same people over and over again, knowing that the people that you've done business with in the past will be the same people that you need to deal with in the future. It's trust that you can build over time. And so, if in your domain you can find those boundaries of trust, you can find some organization, doesn't have to be a government, doesn't have to be a corporation, but just some organization that the membership in that organization is more valuable than any short-term value you might be able to extract by cheating that organization. If you can find that trust within your system, then you can eliminate a whole bunch of the inefficiencies that are built into the blockchain. So, for example, here are some of these solutions that they came up with to try to get around the trust problem is that they couldn't have a merging of history, that they couldn't allow balances to go negative because they wouldn't trust somebody to just not skip out on the system. They had to initiate this proof of work thing and protect against 51% attacks because they couldn't trust somebody to not create a whole bunch of fake history. So all of the rest of these solutions are really good solutions, and the promises that you'll hear about blockchain rely more upon the things that are not crossed out than on the things that are crossed out. So my assertion is that the history of a shared general ledger is not going to be a chain of blocks. It's going to be a directed acyclic graph of verifiable, immutable objects that know about their predecessors. So it's not going to be, it's going to be a graph and not a blockchain. Thank you very much.